The paper I'm presenting is on GUIFUZZ++, Unleashing Graybox Fuzzing on Desktop Graphical User Interfacing Applications. This paper tackles the problem of how to improve fuzzing GUI desktop applications on the Linux systems. It was published in 2025 by ASE, or Automated Software Engineering, which is run by IEEE/ACM. So this is a very recent and cutting-edge paper on fuzzing research. Before getting into the paper, I want to first introduce the authors and their backgrounds to better understand who made this paper. Going through the authors, Dylan Otto is a software engineer at Roblox. He recently finished his undergraduate degree in computer science at the University of Utah, where this paper was the culmination of his undergraduate research. The next author is Tanner Roulette, and he is currently a PhD student at the University of Utah. They both worked in the Futures Research Lab under Stephen Nagy at the time of this work's publication. They were advised by him there. Tanner Roulette was also an undergraduate at the time of this paper's publication, but recently transitioned to pursue a PhD in the same lab with Professor Nagy. Lastly, Stephen Nagy is an assistant professor of computer science at the Calhert School of Computing at the University of Utah. He began his career there in 2022 after graduating with a PhD in computer science from the Forte Research Lab at Virginia Tech, advised by Dr. Matthew Hicks. Dr. Nagy's research focuses primarily on fuzzing. His past work extends from automatic harnessing of fuzzers to better binary fuzzing and faster fuzzing execution through correct target embedded snapshotting. So the first thing to understand before this paper begins is what is fuzzing and what domains has it been applied to currently. Also, why is GUI fuzzing a unique challenge? So software fuzzing is a testing technique to find bugs and vulnerabilities in programs. In a general sense, fuzzing works by taking an initial group of inputs called the seeds to mutate upon and find new, quote, interesting inputs. There are three main approaches to fuzzing: white box, gray box, and black box. Black box fuzzing has no understanding of the underlying source code. Gray box fuzzing has some understanding of the source code through lightweight compiler-based instrumentation, and white box fuzzing has full understanding of the source code and could do more complex operations such as symbolic solving to break through conditionals. Generally, gray box fuzzing is the most popular approach for fuzzing, as it is lightweight, fast, and easy to use. In the above diagram, a simple gray box fuzzing loop is shown. The random inputs are presented as binary, but this can range from anything from structured to unstructured inputs of different kinds depending on the software being tested. So in the case of this paper, the software being tested is GUIs, so the way that inputs are fed in looks slightly different. So the software under test in this diagram is just a .exe file, and it will run this new input, and its output is examined for producing better coverage or potentially a crash. Better coverage means that this input either hit a new basic block, function, or edge that was instrumented in the program. Coverage can also be defined on a more fine-grained scale, where repeated hits to the same instrumentation can make an input seem interesting. This is especially useful for things like loops. The most desired outputs from a fuzzing campaign are crashes. For general testing purposes, crashes are bad for user experiences and the stability of applications. From a security lens, crashes can be used to trigger exploits on a target. While some crashes are benign, they can still allow attack surfaces for actions like denial of service attacks. For more severe crashes, these can lead to memory exploits in languages like C, allowing attackers to potentially use remote code execution to create shells. Software testing by fuzzing can range from simple programs to entire libraries, such as those tested by libfuzzer. This paper focuses specifically on both coverage-guided gray box fuzzers such as AFL++, and also black box fuzzing through a tool like AFL or AFL++. And AFL is just a popular fuzzer, which is shown in the image on the right. It uses coverage-guided fuzzing to find bugs and crashes. and to produce new input, it uses a variety of bit and byte flips, trimming, arithmetic operations, and the like to find inputs. It has also been combined with a variety of custom mutators to allow its usage on different applications, from RTL simulations to this paper's use case, which is GUIs. So now that we have a general understanding of fuzzing, we have to see how GUI fuzzing is a unique challenge compared to fuzzing normal software programs. And by normal, I mean take inputs through either files or just on the command line through standard input. So GUI fuzzing is difficult because traditional fuzzers are not inherently designed to test GUIs. AFL++, a popular open source fuzzer, uses file-based interfaces in order to read inputs into programs. This is done through the command line interface alone, which is not the normal domain of GUI programs. libfuzzer and NYZ target memory-based interfaces like API functions, but these cannot target the entirety of a GUI. GUIs, or graphical user interfaces, are multi-threaded applications where a main thread updates the user interface and issues GUI events to the backend, where worker threads process the requests. It has an inherent separation between what the user views and the underlying process occurring in the background. This thread coordination model introduces a variety of minor bugs and temporal memory errors from different components of the GUI having different life cycles. Current fuzzers exist for some GUI applications, but they are largely limited to mobile interfaces where inputs can be registered anywhere on the screen. The image on the left from Linux shows how, in most applications, there are only select boxes and locations where input can be meaningfully registered. Desktops also have a larger diversity of GUI frameworks such as Qt, GTK, and Xorg for applications. To get around this challenge, some existing fuzzers have attempted to bypass the GUIs through automated programming slicing to redirect inputs to files. This limits the discovery of bugs caused by interactions within the GUI itself. One existing fuzzer is NFuzz, which mutates environmental level interfaces, for example, the config files, fonts, etc., but does not deal with interactions between windows, just data level interfaces. So GUIFUZZ attempts to solve this issue of virtually non-existent functional GUI fuzzers for Linux desktop applications. To tackle this problem, the paper has to overcome 3 major hurdles. So the first major challenge is making a desktop fuzzer that actually interacts with the GUI itself. And this is intended to extend from existing fuzzers with the lowest modifications necessary. And this is especially important for actually having adoption by the wider community. The next major challenge is to overcome the desktop-specific window obstacles. So on mobile applications are in a sandbox with very strict life cycles and a well-known surface for interaction. And this is very different than desktop applications, where applications can have multiple overlapping windows, and these windows can appear and disappear based on interactions by the user. The main obstacle here is to know which windows we should actually be interacting with at a given time, and which we can reasonably register input from the user for testing. And finally, desktop GUIs can't take random inputs, so interactions have to be fairly precise. This means that arbitrary actions or random clicks across the screen are unlikely to hit any actionable components of the GUI. Desktop OSs lack introspective elements, like on Android or iOS, to understand the practical components of applications for testing. So again, GUI fuzzing is important since these are highly complex programs that are used by millions of users daily. And bugs exist across these applications that are very difficult to discover or test, and almost no major attempts have been undertaken to address this understudied area of software testing. The trade-offs of existing solutions to try and shoehorn solutions to use the command line when they weren't built for running solely on the command line just eliminates a major bug surface for testing GUIs, which is the front end that the user sees. So this paper attempts to create a true quote-unquote plug-and-play GUI fuzzer that can be used with existing gray box fuzzers like AFL++. So how do the authors actually implement this work? And so first, we will look at how the first challenge mentioned was addressed, which is how to make a desktop GUI actually interact with a fuzzer. So we need to know how to extend the existing fuzzers in order to provide inputs into a GUI in a meaningful way. So instead of building from scratch, extending from existing fuzzers allows the tool to benefit from existing advances in mutation strategies, speed modifications, and seed selection. Additionally, by extending off of an existing platform in a non-invasive manner, this allows much easier adoption of the tools on the wider market. To extend existing graybox fuzzers like AFL++ to GUIs, the authors present a GUI interaction interpreter. This application reinterprets byte operations as GUI commands. So 3 byte instructions turn into their respective GUI actions. And these randomized actions have proven successful in past mobile GUI application fuzzers. So this is why the authors chose this route. The actions are set up like assembly instructions with opcodes, and these are followed by the data information for the commands. So there are 4 standard opcodes that they use for testing, and the inputs produced by the fuzzer get wrapped to be within this range using a modulus operator. And by using this wrapping and converting other parts of the input into data for each action, this allows GUIFUZZ to work with existing mutation methods with no internal changes. So basically this would just take in the normal inputs and just sit on top of that existing mutation layer. Additionally, the GUIFUZZ queries the windowing application APIs at the start of fuzzing, so it has the screen dimensions of the surface that we're testing on. And this makes sure that the application occurs within a valid dimension and allow for a platform agnostic approach to GUI applications. So on Linux, this querying is handled by the X11 utilities. And the 4 core opcodes of GUIFUZZ++ correspond to the most common interactions for a GUI, which include close window, input data, click location, and drag cursor. So these primitives form a functional superset of GUI interactions to allow wide exploration of GUI behavior using a very limited set. And if there are more specific actions that need testing, these codes can be easily extended with higher opcodes as outlined at the bottom of the table on the left. All right, now on to the next challenge of getting past the desktop-specific GUI problems. So unlike mobile applications, where the application is stuck in a sandbox on the device, where specific locations can be registered for clicks, desktops are quite different. So this means that on mobile devices, you don't have to deal with things like pop-up windows. And desktop GUIs can have overlapping windows from the same application or different applications, and they also appear in different locations across the screen or have overlapping windows from different applications muddling up a screen. So how do we know which windows we're trying to interact with if we're testing? How do we even know which application we are interacting with? If we just click anywhere, we could open up a different application completely that we did not intend to test originally. So to get around this hurdle, the authors record their process PID that initiates the GUI interactions only when the currently displayed window matches that PID. This means that once a test case is complete, the GUI fuzzer knows what the PIDs of the windows are that need to be closed to reset the state before the next fuzzing test case. If other third-party windows are opened, for example, like the update manager, the PIDs of these applications are recorded as well and terminated after the execution of the fuzzing case to provide a clean slate for testing. The application also suppresses dialog windows to protect the file system. It does this by scanning for window tiles with keywords like load, save, and file to bypass those potentially destructive windows. This functionality was built into the GUI interpreter and only needed 2 additional lines of source code added to AFL++ when it was being implemented. So finally, the authors of the paper addressed the most interesting challenge, which is how do we actually maintain precise GUI interactions? And so when I say precise GUI interactions, I mean, how do we actually trigger meaningful interactions instead of just clicking around the screen? So when running a GUI fuzzer with arbitrary actions, it is incredibly likely that you just miss any actionable surfaces or actionable points on the screen. So there are only specific locations on the screen that have, say, buttons or boxes or any actual meaningful input location. And if we had a system that we just clicked random locations with the cursor, it's incredibly unlikely that we would hit anything and we would waste almost all of our test inputs just bouncing around the screen, not really doing anything. So on mobile devices, the SDK or software development kits for Android and iOS devices for Google and Apple provide introspective elements to know where the locations of possible interaction locations reside. So this hinting system makes it very, very easy to set up testing for those designated locations. But there isn't really a good system for this in the Linux desktop environment for testing. So I would argue that the most novel contribution of this paper was the use of software accessibility technology to know where points of interaction can occur. So AT-SPI is an assistive technology service provider interface. So this is meant to aid individuals who need more assistance when using technology with things like screen readers, magnification, or even things like braille displays. So AT-SPI works by displaying the hierarchical view of the application's GUI elements, like say buttons or text fields, to allow accessibility tools to use non-visual navigation of pages. So this technology has built-in support from Linux GUI frameworks like GTK and Qt to allow these introspection features to be extended to actually work with the fuzzer. So some of the AT-SPI specific extensions that were included were for pushing a button, text field entry, checkbox buttons, on or off buttons, radio buttons, spinner buttons, table cell buttons, drop down menus, scrollable fields, or sliding selections. So these greatly expanded the original set of actions that were mostly just based on point and click, as shown in the slide where I was talking about the GUI interpreter. So this also extended the opcodes to a range of 00 to 14 with the modulo wrapping still applied. And then the ATSPI tree, it's also repolled after each application to see where the, or each test to see where the potential next actions can occur. And then the mutator then selects a value from those potential actions based on what's possible in the current environment. So it tries to maximize the chance of having a meaningful interaction with what is currently possible to do on the screen. So now on to the implementation of this experiment. So first, to test the GUIFUZZ system, the authors selected a wide range of GUI applications on Linux. So these included things like graphic design software, animation tools, calculations, image processing, data plotting, 3D modeling, finance, and a variety of tools. So additionally, 3 different base GUIs were used for testing. This included GTK, Qt, and Xorg. Qt was by far the most common, used across benchmarks. So this study had 12 unique benchmarks used for testing. The diagram above shows some of the results for the different setups. What I would like to bring your attention to is the fact that the techniques present do have a strong potential to find bugs, with some runs producing 5 unique bugs on some software such as Umbrello. And as there are currently no other fuzzers that broadly support desktop GUI fuzzing on Linux, there were no competitors they could compare against. So this led the authors to doing a deeper analysis on how fuzzing GUIs compares under different conditions. So this included fuzzing with or without the ATSPI, and then also gray box fuzzing with the ATSPI versus fuzzing with black box, where they didn't have the instrumentation to help guide their mutation. And they also saw that the black box fuzzing without the ATSPI had the fastest execution, which is reasonable because it was doing the least amount of overhead for the actions. And the cost of ATSPI in this also seems to be justified because it achieves the highest code coverage on 9 of the 12 applications, even though it did hurt the throughput somewhat compared to the traditional just gray box fuzzing without it. So focusing on the bug finding results, this is the main purpose of fuzzing applications. So GUIFUZZ++ found 25 new bugs across 12 benchmarks, and these range from things like seg faults to heap use after free to invalid pointers. And some of the bugs have been fixed, and almost all have been confirmed by the developers. To deduplicate the bugs, the authors used address sanitizer based stack trace bucketing. So this makes the deduplication process manual rerun and identification for each of the crashing cases. And of the 25 crashes, 23 were brand new bugs that had never been reported. And then these bugs were found in 11 of 12 tested benchmarks. So interestingly, the only setup which did not find unique bugs was running a black box fuzzer setup with the ATSPI. And this kind of comes from the fact that black box sacrifices better exploration normally for better speed, but then its speed was being hampered by the ATSPI, so it was running without guidance and not as fast of speed. So the two best approaches were running with the gray box fuzzer using ATSPI, followed by using the gray box fuzzer without ATSPI. And lastly, onto a little bit of end discussion. So in summary, this work bridged the gap of functional GUI fuzzing tools for a Linux desktop environment because none existed before this that were actually usable. So there were existing fuzzers for applications on other operating systems, specifically on mobile like Android and iOS, but no alternatives for Linux. For Linux on desktop. To overcome this problem, the authors intended to create an efficient fuzzer which would be able to explore the GUI itself to trigger actions that uncovered bugs. And this was done through using both gray box and black box fuzzer setups that were combined with software accessibility technology to better understand which parts of the screen were available for interactions. This went alongside an interpreter that converted the bytes into actionable GUI interactions to better explore the applications with existing fuzzer setups. Lastly, this paper found 25 bugs in Linux GUI applications. Future work plans to extend the clicking functionality to both left and right clicks instead of just left clicks, and they intend to generalize this approach to other platforms, and they believe that this approach could be applied to other fuzzers outside of just AFL++ where this was implemented. So, thank you for listening to the presentation.